Hi there, everybody. Welcome to another Chem Complete lecture in the General Chemistry series. And today we are going to take a look at the beginnings of thermodynamics and the study of thermodynamics. And more specifically, we're going to take a look at energy, the units that define energy and the types of energy, as well as the first law of thermodynamics. And this will be a lead-in to enthalpy, entropy, and free energy, which are the three main components that we study when we are looking at thermodynamics. So get ready for your intro to thermodynamics on the channel coming up right now. Thank you so much for choosing Chem Complete for your learning needs today. Now let's go ahead and get started. So what we are going to take a look at first here is energy, because this is usually the first time that students encounter energy in a general chemistry class, outside of when you're doing your SI units in the first opening chapter. So when we get to thermodynamics, the units that we use for energy, the SI, or the Standard International Unit for the metric system, is joules. That is what you will come across most often. And then a secondary unit that will still appear quite often is calories. And calories is noted with a little c here because calorie, from the thermodynamic sense in its pure energy definition, is different than a calorie from the food sense. So I just want to lay that out at the beginning here. A kilocalorie, if you're over in Europe or some other place, or a calorie with a capital C, if you are in the United States, which is your food calories, make up 1,000 of these smaller calories that we are going to define here today. So take food calories and kind of put that out of your mind when we're discussing this. They are certainly interrelated through the metric system, but they are not the same thing here. So a joule is the main unit, and 1 calorie is equal to 4.184 joules. And that may seem like a bizarre value that's kind of random, but it does have basis in thermodynamics and energy calculations. And 4.184 joules is the energy that is required to raise 1 gram of water by 1 degree Celsius. So this is also known as the specific heat, or the heat capacity, that we assign to water. And we will have a lecture down the road here that takes a look at specific heat or heat capacity and how to calculate those things based on mass, temperature differences, and the specific material that you are looking at, whether it's water or some sort of a metal like aluminum or iron. You can make those calculations, okay? But for right now, 1 calorie is equal to 4.184 joules. Now, the energy types. There are 2 main energy types that we come across when we look at physics and thermodynamics. So the first is kinetic energy, and the second is potential energy. Now keep in mind, because we are focusing in relation to chemistry right now, we're going to kind of try to keep in scope or define these within chemistry parameters. So kinetic energy is the energy of motion. So in a classic physics class, you might see a ball that's being thrown or something of that nature. When we are looking at chemistry, we're looking at the energy of motion in relation to molecules that are moving in a system. So molecules are constantly in motion. Even when they're in the solid state of matter, they're vibrating against one another. And then as temperature will start to increase, the movement will become more rapid, the molecules will become more spread out, and eventually you can start having collisions between molecules, which is how we can get reactions to start occurring. Now, potential energy, on the other hand, is the complement or the opposite to kinetic energy, and it is the stored energy due to the position of some sort of material. Okay, so again, if let's say that the ball that was being thrown in physics is placed up on a shelf and it is a certain height from the floor, it would have some amount of potential energy based on its position relative to the floor. Okay, or in chemistry, which again is what we're focused on here, it will be due to structure. And more specifically, we're looking at the bonds that are making up specific molecules, so the stored energy that is found in those bonds. And that is how food works. When we consume food for energy, a lot of people in the mainstream or the general public just know, oh, you have to eat and that gives you energy. But it's really, when we look at the carbohydrates and the fats and the proteins that make up the food, we end up with stored energy in those chemical bonds. And the body can break that down using various enzymes and the acid in the stomach and mechanical digestion through chewing or the stomach churning and so on. All right, so again, kinetic energy we're going to be viewing as molecules moving throughout these lectures, and then potential energy we're really going to be looking at the stored energy in bonds. Now, there are several other important factors we want to cover or discuss in our introduction to thermodynamics, and the first two are very closely related. There is the law of energy conservation and the first law of thermodynamics. And in fact, they're so closely related that one will often be conflated with the other. So many people, when they are asked what's the first law of thermodynamics, they essentially give the law of energy conservation. And that is true, but you have to keep in mind that there are different types of systems. So we'll discuss all of that here in just a minute. All right, so starting with the law of energy conservation, energy may be converted between different forms, but the total energy that is within a system must remain constant. Now, there are certain parameters to this, especially if you have an open system, you can have exchange of energy. However, all of it should be tracked, and another way of stating this law is to say that energy may be converted or transferred back and forth, but it may never be created or destroyed. That's the one that you typically hear more often from the general public or people that have some general knowledge of the thermodynamic laws. All right, now the first law of thermodynamics, which again is very closely related, says that the change in the internal energy of a system that we are studying is the sum of two things. It's going to be the sum of the heat that is either leaving the system or coming into the system, and the work that is done by the system. Okay, so we're going to get into definitions here. You can see them right below. We have system and surroundings. And so it is technically the work done by the system on the surroundings. Now, the surroundings could also do work on the system, and that is another possibility there. All right, but that's the first law of thermodynamics, and we will cover the second and the third law. And we'll even mention the zeroth law in its own video, because there's a zeroth law of thermodynamics related to thermal equilibrium. So what is system and surroundings? A system in chemistry is going to be a reaction or a reaction vessel that is of interest. So in other words, it's what you are going to be studying as the researcher. And most typically, this is going to be a specific reaction. You are interested in the thermodynamic parameters that govern that reaction. Is the reaction going to be spontaneous? What's the entropy of the reaction? Will it be endothermic or exothermic? And if all those terms don't make sense right now, that's okay. We're going to go through them as we cover the thermodynamic lectures here on the Chem Complete YouTube channel. So surroundings, you can see is a very simple definition, is literally anything outside of the system. So if I am looking at a system in thermodynamics, the surroundings is anything that is outside of the system that I am currently studying. So yes, that is a very broad definition, but that's because the surroundings technically are broad. We could go all the way up to the parameters of the known universe as far as the surroundings, and that could constantly be expanding as you are looking at the boundaries of the universe expanding outwards and continuing in its infinite journey. Okay, so this is a very important part here. We have to classify or discuss some different types of systems in thermodynamics, because this will help govern what may or may not be possible in a certain situation. So there are really three systems that we can consider or hypothesize in terms of thermodynamics. The first one, and probably I would argue the most common one that we see in everyday life, is an open system. So an open system is a situation or a system where matter and energy, both of them, can be exchanged between a system and its surroundings. So not only can energy itself be transferred back and forth between the surroundings and the system, but matter is free to leave the system, and matter is also free to enter the system. Now, on the other hand, a closed system is where only energy can be exchanged between the system and the surroundings, but matter is not going to readily be able to come in or cross over. So if you had some sort of, let's say, an airtight cooler or thermos that is not going to allow anything in or out, and you just leave it there, we know that the energy is going to be able to be transferred out of the system and to the surroundings, because let's say that I take some hot coffee and I put it into a thermos. That thermos may do a very good job at insulating it for several hours. It could even be upwards of a day, depending on how efficient it is. But eventually, it is going to come into thermal equilibrium with the surroundings, meaning the heat that is within that thermos or that chemical system within that thermos is going to transfer out to the cooler surroundings, right? The environment around you, the room that you're in, or maybe you put your thermos in your car or something like that. And so you have to realize that the energy can still leave a system like that. However, we are not allowing coffee out of the system. Now, we're assuming we're not opening it and drinking it or something like that, because then it would become an open system. Okay, and then we also do not have anything from the outside environment that is coming in or filtering into that system, provided it is truly closed. And the last type of system is called an isolated system. Now, in an isolated system, you do not have exchange of energy or matter between the system and the surroundings. So this is only theoretical in nature. We have developed very, very strong systems, robust systems in terms of the ability to try to not let energy out. However, in theory, these are only theoretical. We do not have perfect isolated systems that exist. The only case you might be able to make for that is if you're looking at the entire universe at a given point in time, because keep in mind it's constantly expanding, and that entire universe is your system. Well, then everything contained within it would stay there, and it's really isolated because you technically don't have surroundings, or the surroundings are kind of on the cusp or constantly being evolved out as the universe is expanding. All right, so to start wrapping up here, because the next topic, we're going to take a deeper look at heat and enthalpy, which is the first of one of the three main components or measurements. They're technically called state functions, which we will define in the next lecture. Okay, so what is heat? Heat is represented as lowercase q when we are studying it in chemistry. And heat is going to be the energy that will be transferred into or out of a system that results from a temperature difference that is between the system and the surroundings, right? So let's say that I have a really hot oven and I open the oven up. There's a big temperature difference between the outside surroundings and the heat that is in that oven. And so when we feel that blast of warm energy that basically hits us in the face, right, that is a result of the energy movement, because there is a temperature difference or kind of a temperature gradient, right, that starts to form as it begins to travel. So it is very important to realize that heat does not equal temperature. And a lot of people think about this, and it's, you know, it's understandable given the everyday vernacular that we use when we say it's hot outside, or it's, you know, there's a lot of heat today. You're talking about or conflating temperature with the actual energy related to the term heat. So heat does not equal temperature, which then we just defined heat. That asks the question, what is temperature? Temperature is the average kinetic energy for the molecules that are within a system. So you're basically looking at those molecules and how fast they're moving, and you are taking a metric measurement of the average kinetic energy for those molecules. So temperature and heat are very closely tied to one another, but they are not the same thing. And that is the last major important takeaway from our introduction to thermodynamics lecture here. So that covers what I wanted to discuss in this initial set of energy and first law of thermodynamics. It's a good intro to thermodynamics, and again, we'll continue with enthalpy next time. So head on over to chemcomplete.com. You can get lots of free resources to help you with your studies over there. Like the video if you found it useful. It always helps to support the channel and boost us in the algorithm. If you subscribe, you will stay up to date with all of the releases as you continue your learning. And as always, if you comment, I will try to get back to you if you have any questions. So chemcomplete.com, one more time, is a great way to support the channel, and I will see everybody in the next lecture. Thanks for learning with me.